All right, let's dive into computer vision today. We're looking at excerpts from Szeliski book 210903 draft.pdf.
Yeah, it's a foundational text in the field,
Really helps us understand how computers learn to see.
which, as you know, is way more complicated than it sounds.
Yeah, for sure. So where do we even begin?
Well, the book breaks it down into three core pillars, kind of like a roadmap. We've got the scientific approach,
Right.
then there's the statistical side of things.
Huh?
And what's really fascinating, the book also emphasizes drawing inspiration from, how humans solve visual puzzles.
Three pillars. Interesting. But break those down for me. What's involved in each one?
Sure, the scientific approach is like detective work, building mathematical models to understand how images are formed.
Like how light interacts with objects and all that.
Exactly. It's like reverse engineering the whole process our eyes and brains do without even thinking.
So instead of dusting for fingerprints, we're tracing photons.
Exactly. Then you've got the statistical approach, which is all about dealing with uncertainty. Real-world images are messy.
Right. Noisy, blurry.
Yeah, and there's often missing information. So this approach uses probabilities.
To fill in the gaps.
Yeah, make educated guesses based on the evidence. Like solving a puzzle with some pieces missing.
I'm starting to see the picture. But what about that third pillar? The human element.
Well, the book highlights how humans are naturally good at these visual puzzles. We understand context, we can infer what's missing.
Right. We see patterns and make connections.
Exactly. So researchers are now exploring how to translate those abilities into algorithms.
Trying to teach computers to think like we do, visually speaking.
In a way, yeah. Which brings us to a really crucial concept the book emphasizes: vision as an inverse problem.
Okay, now you've lost me. What's an inverse problem?
Well, think about speech. We have a pretty good understanding of how sounds are produced, right?
I guess, yeah.
But with vision, modeling the entire visual world with all its complexity, it's a completely different ballgame.
So it's easier to figure out how someone said a word than to understand what they're looking at.
Basically, yeah, we have to make assumptions, rely on probabilities. It's a constant puzzle.
Speaking of puzzles, the book talks about some amazing progress in creating 3D models from images.
Right, like techniques like multi-view stereo and silhouette-based reconstruction.
So imagine taking a bunch of tourist photos and creating a perfect 3D model of a building.
Exactly. It's leveraging information from different perspectives, like our two eyes do for depth perception.
So it's all about triangulation, piecing together the visual puzzle from multiple viewpoints.
Precisely. And underpinning all of this are mathematical transformations. Rotations, translations, scaling.
The stuff that makes my head spin.
Well, it's the language computers use to understand how objects move and change in 3D space.
Okay, so give me a real-world example. How are these transformations actually used?
Well, think about augmented reality, those apps where you place virtual furniture in your living room, right?
Yeah, I've played with those. It's like magic.
It is pretty cool. And those transformations are what allow those virtual objects to stay put, even as you move your phone around.
So they're like the anchor connecting the virtual and real worlds.
Exactly. And of course, we can't forget about light and color.
Yeah, those seem pretty important for, seeing.
Absolutely. They influence how we perceive shape, texture, even emotion. The book goes into models like the BRDF.
Oh, what?
The BRDF, bidirectional reflectance distribution function. It's a way to simulate how light scatters and reflects off different surfaces.
Sounds complicated.
Well, think about computer graphics, like video games and animated movies, to make things look realistic.
You need to understand how light bounces off different materials.
Exactly. That's where the BRDF comes in, providing the mathematical framework for those amazing visual effects.
So the BRDF helps computers understand how light plays on surfaces, making virtual objects look more believable.
Right. And it's not just about visual realism. It can also be used to, figure out the lighting conditions in a photograph.
Wait, you're saying we can tell where the light sources were just by analyzing the way objects are illuminated?
Yep. Pretty amazing, right? And speaking of tools, we can't forget about the digital camera.
I kind of thought that was a given.
Well, the book highlights how all its inner workings, the exposure control, color correction, all that, it directly affects the images we analyze.
So the camera isn't just a passive observer, it's actively shaping the data.
Absolutely. And understanding that is crucial for computer vision algorithms.
Yeah.
Even something like camera noise, which we might not even notice.
Can throw those algorithms off?
Exactly. Then we get into filtering techniques, which are essential for tasks like smoothing, sharpening.
Oh, like those filters you use on Instagram.
Kind of, but in computer vision, they're more like specialized tools to help identify important features and patterns.
Okay, so what kind of filters are we talking about?
Well, there's the Gaussian filter, which is used to smooth images and reduce noise.
Gaussian filter. Sounds familiar.
Think about removing graininess from a low-light photo. That's the Gaussian filter at work.
Ah, so it's not about making the image pretty, it's about preparing it for analysis.
Precisely. Then there's the Laplacian of Gaussian, or log, which is great at edge detection.
Edges. Why are edges so important?
Well, think about how we recognize objects. The edges define their shape, right? The straight lines, the curves, those are key clues for algorithms.
So edge detection is like giving computers X-ray vision, seeing the outlines of objects, even in cluttered scenes.
That's a good way to put it. And this leads us to an interesting concept, global optimization for vision tasks.
Okay, now you're just using big words to scare me.
No, it's actually pretty intuitive. Imagine a giant jigsaw puzzle. Global optimization is about finding the absolute best arrangement for all those pieces.
So everything fits together perfectly.
Exactly.
Yeah.
And in computer vision, many problems, like image segmentation, can be framed in this way.
Image segmentation, what's that?
It's basically dividing an image into meaningful regions based on things like color or edges.
So like separating the foreground from the background?
Exactly. Techniques like graph cuts come into play here.
Graph cuts. Are we actually cutting up graphs with scissors?
No. It's a mathematical technique to, separate an image based on certain criteria.
Okay, but why is image segmentation so important?
Well, think about self-driving cars. They need to be able to distinguish the road from everything else, right?
So without image segmentation, a self-driving car wouldn't know the difference between the road and, say, a pedestrian.
Exactly. And that's just scratching the surface of how global optimization is used in computer vision.
Wow, we've covered a lot of ground. From light and color to filters and optimization techniques, my head is spinning a bit.
It's a lot to take in, for sure.
So what's next on our computer vision adventure?
Well, next time we'll dive into even more applications, things like motion estimation, image stitching, and the whole world of computational photography.
Sounds exciting. I'm ready to see where this takes us.
Back again for more computer vision.
A brain still processing everything from last time.
It's pretty wild, right? How much goes into replicating something we do so easily?
No kidding. And we just scratched the surface. You mentioned motion estimation and image stitching. Those sound like game changers.
They are, absolutely. The book talks about how they're revolutionizing things like video analysis, even robotics.
Okay, so motion estimation first. What's that all about?
Imagine watching a tennis match, right? Motion estimation is figuring out how the players, the ball, even the camera, how they're all moving.
So it's not just seeing objects, it's tracking their movement over time.
Exactly. And this is huge for all sorts of applications. Self-driving cars, for example.
Oh, right. They need to know where everything is going.
Exactly. They have to constantly analyze the motion of other cars, pedestrians, everything to navigate safely.
So it's like giving them a sixth sense, predicting what'll happen next.
That's a great way to put it. The book mentions some cool algorithms for this, like Lucas-Kneed and optical flow.
Names ring a bell, but remind me what those do.
Lucas-Kneed is good for tracking specific points. Say a car's driving down the street. You could use Lucas-Kneed to track its corners.
As it moves, so you get a sense of its speed and direction.
Right. Useful for all sorts of stuff. Stabilizing shaky video, creating special effects, even predicting where that car is going to go next.
Pretty slick.
Yeah.
What about optical flow, though? How's that different?
Optical flow is more about the bigger picture, the overall movement in a scene. It estimates how every single pixel is moving.
Oh, so it's like a map of the whole flow of movement in a video.
Exactly. Super valuable for things like analyzing fluids, tracking crowds, even reconstructing 3D scenes from a video.
Okay, that's just blowing my mind. We're talking about unlocking the secrets of motion itself.
We are, and motion estimation is just one piece. Let's talk image stitching, another way we're changing how we see visuals.
I do that on my phone all the time.
Yeah.
Making panoramas.
Panoramas, exactly. That's a perfect example. But think bigger. Google Street View, right?
Oh, yeah. Those 360 views are insane.
They use image stitching to create those, combining thousands of pictures.
So it's like creating one massive image from a ton of little ones.
Precisely. And it's not just slapping them side by side. There are algorithms to align them perfectly, correct for distortions.
Distortions, like from the camera lens.
Exactly, like those fisheye lenses that create that curved look. Kind of fix that for a seamless panorama.
So it's like ironing out the wrinkles before you sew the pieces together.
Love that analogy. And image stitching isn't just for panoramas. Medical imaging uses it too.
To get those really detailed images of, like, the whole body.
Exactly. So these techniques aren't just for cool visuals, they're helping with research and medicine too.
That's incredible. It's not just how we see the world, but how we understand it that's changing.
It really is. Speaking of pushing boundaries, let's talk computational photography.
Now we're getting fancy. This sounds like sci-fi stuff.
It's actually all around us now. Think about HDR, high dynamic range imaging.
Oh, yeah. Those photos that are super vibrant and detailed.
That's it. HDR takes multiple shots at different exposures and combines them so you keep all the details.
Highlights and shadows, all in one shot.
Precisely. And there's more. Tone mapping, for example. Adjusting brightness and contrast to create certain effects.
Like those filters that make photos look old-timey.
It can do that, but also just make images more realistic. Capturing the full range of light, like in a sunset, without losing anything.
So enhancing the photo by playing with the tones.
Precisely. The book also gets into things like image matting, which lets you extract objects from the background.
Oh, like in Photoshop when you cut something out.
Exactly. Image matting is how we do that. Algorithms analyze the colors and edges, creating a perfect mask.
Like digitally peeling the object away from the background.
Exactly. Image matting, HDR, all of this is blurring the lines between photography and computer graphics.
We're in a whole new era of image creation. The possibilities are endless.
It's an exciting time to be exploring this, that's for sure, and we've only just scratched the surface.
Well, I'm hooked. What else does the book have in store for us? Back for the final leg of our computer vision journey. Motion estimation, image stitching. We even touched on computational photography.
We've covered a lot of ground, but there's still so much to explore.
Right. Before we get too artistic, though, you mentioned 3D shape recovery. That sounds like a whole other level of visual understanding.
It really is. Think about it. We humans, we just see things in 3D, no problem, even from a single viewpoint.
Yeah, it's easy to take for granted how amazing that is.
And now researchers are trying to give that ability to computers, teaching them to infer 3D shape from flat images.
Wait, so you're saying computers can learn to see depth in a 2D picture? How's that even possible?
There are some really clever techniques out there. The book talks about shape from shading, for instance.
Okay.
It analyzes how light and shadow fall on an object, and from that, it can figure out its 3D structure.
Like a detective using clues from the light to solve the case of the object's shape?
Exactly. There's also photometric stereo, using multiple images under different lighting.
Like taking a bunch of mugshots of the object and using that to build a 3D model.
Precisely. And then there's structure from motion, analyzing images from a moving camera to create a 3D model of the scene.
So like if I'm driving down the road taking pictures, a computer could build a 3D model of everything I saw.
That's the idea. It's used for everything from mapping cities to exploring other planets.
Wow, it's like bringing the third dimension into the world of computer vision.
A complete game changer. And this 3D shape recovery is a stepping stone towards something even more exciting: object recognition.
Now you're talking. That's what I'm really interested in. It has so much potential, right? From self-driving cars to medical diagnoses.
It really does. Object recognition is all about identifying and classifying objects, whether in images or videos.
So it's not just seeing an object, it's knowing what it is.
Exactly. And to do this, you need to train algorithms on huge data sets of labeled images.
Like teaching a kid with flashcards, showing them a picture and telling them what it is.
That's a good analogy. And the book goes into different techniques for object recognition, things like eigenfaces, deformable models, even deep learning.
Eigenfaces. Deformable models. Okay, those are some fancy terms. Break those down for me.
Sure. Eigenfaces are specifically for faces. They analyze lots of face images to find the most important features.
The features that make each face unique.
Right. And then they can use those to recognize new faces.
Okay, that makes sense.
Yeah.
What about deformable models, though?
Those are more versatile. They can be used for all sorts of objects. Basically, you create a template, like a car or a hand.
And then it can adapt to fit different versions of that object.
Exactly. So it works even if the viewpoint changes or the lighting's different, or even if part of the object is hidden.
That's impressive. Now, what about deep learning? I feel like that's everywhere these days.
It's really taken object recognition by storm. It involves training these massive artificial neural networks.
Giving a computer a super brain and letting it figure out object recognition on its own.
Kind of, and the results are astounding. Deep learning algorithms are sometimes even outperforming humans.
Seriously. That's both exciting and a little scary.
It is, but it just shows the incredible potential of computer vision.
We've come a long way in this deep dive, from light and color to 3D shape recovery, and even object recognition. My mind is officially blown.
It's been quite a journey, that's for sure. But it's amazing to see how computer vision is changing the world around us.
Absolutely. It's not just about understanding images, it's about understanding our world in a
Yep.
whole new way.
Exactly. And as these technologies continue to develop, who knows what the future holds? It's an exciting time to be following this field.
For sure. And for our listeners who are just as fascinated by this as I am, I can't recommend the Szeliski book enough.
It's a dense read, but it's well worth the effort.
Absolutely. Well, that brings us to the end of our deep dive into computer vision. Thanks for joining us on this incredible journey.
It's been my pleasure. And remember, keep exploring, keep asking questions, and who knows, maybe you'll be the one making the next big breakthrough in computer vision.
Until next time, keep your eyes open to the wonders of the visual world and the incredible ways we're learning to see it.